Alright, so what happened in the last example where we ended up with the same thing that we started off with, or a couple examples ago, it's very, very common. I want to show you another place where it happens. This is a typical biparts problem. This is not even a hard one, but it exhibits that same phenomena where you end up with the same thing you started off with. Again, the idea is going to go something like this. You're trying to solve for A, that's the one you don't know, and then you got some stuff here, and then you end up with something like minus A. The trick here is to add A to both sides. You add A to both sides, and this goes away. Now you have 2A's is equal to that stuff. And then this is just algebra. There's absolutely nothing fancy going on here. This is just elementary school algebra. You take a half on both sides, and you get that A is equal to a half of that stuff. Right? That happened a couple examples again, and I want to do this problem where it happens again so that you become really, really comfortable with this idea. Every time you end up with the same thing you start off with, say, whoa, that's awesome. I can swing it over to the other side, I'm done. The only time where that might not happen is if you have A is equal to some other stuff and then you get plus A. That's a special case because if you try to go and subtract these things, you get that 0 is equal to all that stuff. So I hope that stuff that you got there is 0. It usually means the technique didn't work and you've got to try something else. But as long as that's not the same as the left side, a plus A and a plus A, if you've got a constant here like 5A's or any other thing other than just 1A like you have on the left side, when you subtract it, you won't have 0A's. You'll have something good. Okay? Anyways, talk is cheap. Let's do this problem. So, not that one. So let's do this problem here. Let's erase all this. Time machine. That will be gone in 3, 2, 1, 0. Alright, so we're ready to start off on this problem. The only thing you got to do is make a good choice for you, and the rest of it has got to be determined by whatever's left over. So I'm going to go with u is equal to e to the x. That I cover it, that forces whatever's left over to be dv. So I have cosine of x dx. That way the expression here is in fact equal to the expression there, a u and a dv. And this becomes I have to finish the dictionary here. du is equal to e to the x dx. v is equal to sine of x. Take the derivative here on both sides, take the antiderivative here on both sides. That completes the dictionary. That leaves us to be vu, e to the x sine of x minus integral of v du, so it will be e to the x sine x dx. That's these two together, v du. And then you say, whoa, how do I do that? That seems just as difficult as the original problem, which was e to the x cosine of x dx. And you may have a good case for being concerned, but being human that we are, we never give up, we just keep trying. So we could try something else here. Maybe I try a u is equal to e to the x and a dv is equal to sine of x dx. That would force du is equal to e to the x dx. So what I'm doing is the second by parts. By parts again. The previous one was so fun, I'm going to do it again. And so I have this, that the derivative, cosine, I think I need a negative here so that when I take the derivative I get dv is equal to that. Alright, then that would lead me to believe that the integral of e to the x cosine of x dx is equal to e to the x sine of x minus, okay, I got this big old thing here, I'm going to need some space, vu, so I have negative e to the x cosine of x minus integral, well I have a minus there, it'll give me a plus, cosine of x, wait I need e to the x there, e to the x cosine of x dx. That's this piece right here, on this little biparts, on just that piece alone, that's what we get for that expression. Okay, I have to distribute this negative and clean it up, so I get that the integral of e to the x cosine of x dx is equal to e to the x sine of x plus e to the x cosine of x minus integral of e to the x cosine of x dx. And then you wonder, whoa, wait a minute, time out, I'm getting the same thing I started off with at the beginning. This is exactly the same problem I had at the beginning. Luckily here this is a minus, So if I was to add a couple of these on both sides, let's make it yellow. So I'll add the integral of e to the x cosine of x dx on that side, and I'll add the integral of e to the x cosine of x dx on that side. What will happen is I will get, see if I can get us some more room here to spread our wings. Alright, I'll get two of these. I'll get two integrals of e to the x cosine of x dx is equal to ex sine of x plus ex cosine of x plus 0. Say, whoa, even now I can solve for this. All I gotta do is slap a 1/2 on both sides, and we're good to go. E to the x cosine of x dx is equal to 1/2 e to the x sine of x plus e to the x cosine of x plus a constant. Duh. It's a nice problem here because it has a couple things that are more interesting than the usual ones. For starters, we have to do by parts twice. Again, it's nothing new. Sometimes you may have to do it 5 or 10 times. But this gives you a little flavor where you have to do it more than once. And second, it helps you practice that boomerang idea where the thing you start off with, boomerangs, comes back on the other side. And you have to add it to both sides to cancel it. That's why this is a nice problem, nice example. Right? Alright, but that's nothing. Wait till you see what's coming up. We'll turn it up a notch or two in the next couple examples.